right, thank you for your patience. We're going to be doing a live demo, so we needed to switch out the laptops. I'm Jonathan Payne. I'm the Executive Director for the Open Concept Lab and an affiliate at the Regenstrief Institute. I'm thrilled to be presenting today on the OCL Mapper. OCL is the Open Concept Lab. It's an open source community that develops and designs and implements terminology management tools globally. The OCL Mapper is a next generation terminology mapping solution for the post-Roma era. I'm going to be presenting today with Joe Amlung, who many of you already know is Senior Technical Advisor at the Regenstrief Institute and a longtime product owner with the Open Concept Lab, and also Michael Bontyes, the Director of Programs and Digital Health at Madiro and a consultant with MSF. And I'm presenting on behalf of a lot of organizations that have worked on this project in the last 10 months, and you can see many of them here right now. I'm here today also as the founder of OCL, and like a lot of communities of practice, OCL started as a one-person passion project to bring data standards and the benefits that they have to communities that need them most. And so that was primarily in global health contexts. And over a decade ago when this started, what that looked like is a lot different than what the world looks like today. And we were on the verge of shifting from management of a lot of infectious and communicable diseases to the idea of eradication, and especially thinking about HIV. And governments, donors, partners were investing heavily into data exchange architectures because of the requirement of information to get to that last mile. To get from 90% eradication to 100. There's a huge difference in the amount of data and the speed and the place and the timing of that data that you needed. That's when OCL grew from a one-person project, that was me, to a global community practice with users, implementers, terminologists from all around the world. But the world looks quite a bit different now. And some of that progress, some of that investment is at risk. And this is the context in which we are trying to introduce a new tool that we believe is going to be more useful than ever to a lot of communities that still need to do more, but now with less resources available to strengthen their health systems and the exchange data to support that. So this, again, excited to introduce this tool then to you. But first, an exercise. If I can figure out how to get this to work. There we go. Okay, so this is a terminology mapping project. And so we'll start with the terminology mapping challenge. I'll give you a second to read through this. We're trying to map the test. This is a CBC order with platelets. And so the first thing we'll do is get some candidates. And again, we'll give you a second to take a look and see if you can try to identify the right one. Anybody already getting close? I imagine Pam might be, but you're just shy about raising your hand. I see a couple. Okay, so this is not an easy process to do quickly, is it? And especially, you probably all want to know a lot more information about each of those candidates. And clicking on each one, reviewing the details takes some time. What if there was an AI assistant that could help you with that process, that could tell you where the axes line up with those candidates from your input data and give you rationale that you can use to streamline your process? So this one here is saying that we want to look at a particular code, 265157, and it tells you specifically which properties are aligned. So it's the exact component, the correct system, appropriate property, matching units. Says there's consensus across the algorithms that were used to generate these candidates, and the rationale goes on. And imagine if you had this when you're doing your mapping projects. And so it then pointed to number 8. It gave a strong recommendation for that, and you were able to make the mapping decision. So this is the workflow that we're going to talk about today, introducing this capability into your mapping projects for LOINC and perhaps terminologies beyond LOINC. So what problem did we set out to solve? First is the mapping bottleneck. terminology mapping is a huge bottleneck worldwide. This is true in all contexts, low, middle, high-income countries. There's the specificity challenge. LOINC struggles with this in particular because of its pre-coordination, makes it more difficult to map to, and that makes automation even more challenging. And so, especially to get to an unambiguous, strong recommendation versus maybe a set of possible candidates. This often leads to the use of more generic LOINCs, which can, of course, cause downstream risk. The technology available to do this mapping with LOINC, some of it's outdated, some of it's cost prohibitive. RELMA, as an example, is still the gold standard for mapping a LOINC, but it's showing signs of age. And finally, the capacity shortage. Terminologists, like all of you, are unicorns in the world. They're very rare, and in all settings, in work that we've done in global health contexts, it's not uncommon for there to be no terminologists involved in the project or even staffed at the Ministry of Health. This week, I've learned from some of you that that's also true in high-income settings. So this is not a unique problem. So in short, there's no terminology mapping solution today that's available that is open source, collaborative, terminology agnostic, and AI enabled. So that's what we're going to talk about. So I want to introduce you to the OCL Mapper Squad. This is a few people that I'll be talking with today, some other friendly faces that you know from the LOINC community, I think a couple that are here virtually with us, that we set out to launch an open source mapping tool that uses AI to support its matching algorithms that could work with any terminology, but starting specifically with test cases around LOINC and CIEL, which is an interface terminology commonly used in global health contexts. So what is OCL? I described a little bit of the origin. It's an open source community that develops terminology management solutions and supports their implementation. It's open source, cloud-based, community-driven, standards-based, not just the data standards, but even FHIR, and also globally adopted. We have users from all over the world that have either self-deployed or are using our cloud-hosted solution. A couple examples of that. So Kenya's National Health Terminology Service is powered by OCL. Brazil's FHIR-based IPS exchange uses OCL for terminology management and translation. The OpenMRS community, so open source medical record system, is most commonly used EHR in low-income settings. OCL is the preferred concept dictionary management solution for that, which means that OCL is used to manage metadata that's used in thousands of health facilities across the world. I encourage you to take a look at these links when you have a moment to get more information about any of these projects. So what's the organizational journey that we're looking at, that we're trying to help solve? And we use this paradigm of map, manage, and use. And so an example, maybe in the lab context, is a lab analyst is mapping a LOINC, a new instrument. The medical director is updating the entire mapping table with a new release of LOINC for consistency and accuracy. Your engineer or informaticist might be doing an integration for reporting requirements to the terminology service. So OCL offers tools for each of these steps in that paradigm. The OCL Mapper, which we'll talk about today, the term browser, and the FHIR service. These are all powered by the terminology server in the back end. And encourage you to take a look a little bit more at these in our website. The Mapper, we're really focused on collaborative mapping with AI. The term browser, this is our V3 tool that's under development. So you can already access it, but the V2 one that's already in production is the one that is fully functional. It's the next generation terminology management platform. FHIR service for integrations in your business workflows, and then our REST API-based terminology server. So when you bring all these together, it starts to introduce capabilities that I call terminology intelligence. And so what does that offer you? It lets you use natural language to help you work with terminology smarter and faster. A great example that Michael will talk with you a little bit more about in a moment is what if you could say to your favorite AI tool of choice, such as Claude, and say, go get my concept dictionary, identify all concepts that do not have a French translation, generate a fully specified name in French for those, and go ahead and submit it back to the terminology server, and then let me review that and save hours and hours of time. Another example, it's multi-server capable. You could ask it to synchronize value sets across terminology servers. I'm going to move into some that are more aspirational. A lot of these are still being worked on, but I hope you get the idea of the direction where this is going. FHIR modeling, you could load in a FHIR questionnaire, say, identify answers and questions that are already part of my code system and those that are missing, propose the model for the concepts that are missing based on the structure in the questionnaire. You can do QA on existing terminology content that you have. or even start to do more complex things like cohort building and subsumption. So really excited to kind of go into this more. If you join us in the roundtable discussion this afternoon, I think this could be a topic that we talk about. These are exposed APIs through an MCP server, which is how you give AI tools. All of the matching capabilities that we'll talk about shortly are also exposed through the MCP server. So looking more at the OCL Mapper itself, the starting point is lexical matching. You need to match your keywords. And so this is something that Relma already does very well. So OCL Mapper also introduces that. But we've also introduced semantic search. Semantic search looks, instead of specific words, it looks at the meaning, tries to match based on those. So this is how you could say heart attack and match against myocardial infarction. And it uses technologies called semantic or vector embeddings and cosine similarity search. Those are really important technologies in AI, and once you've started down that path, you can start to take a bit advantage of more advanced capabilities that AI offers as well. AI Assistant is what helps you streamline your mapping process, can review your candidates and provide recommendations. It supports matching as a service. You may have your own matching algorithm already. What if you could just wrap that around a compatible API, and then you could connect it to a general purpose mapping user interface and take advantage of those collaborative workflows. It's multilingual. Right now, Relma is multilingual, but the burden is on the publisher to define all of those translations. That's an enormous burden and maintenance task. Through cross-lingual embeddings, you could use, say, a French input term and search directly against English target concepts without any translation step in the middle. Today, those cross-lingual embeddings are not generally trained on medical terminology, so they have less specificity for medical vocabulary, but you can understand why that's still a lot of value there. It supports matching based on properties, based on cross maps that might be in your input data set. Bridge terminology matching, so through the CIEL interface terminology that already has maps to other vocabularies such as LOINC, you could expand the lexical variance of your semantic searches using terms that are available in CIEL. And we'll get to look at an example of that shortly. Multi-terminology support, so not just LOINC, but also other vocabularies, collaboration, and it's integrated into the rest of the OCL Enterprise Toolkit, meaning that there are lots of other terminology capabilities available if you were using this. However, it doesn't support everything that Relma supports. And so Relma has been around a long time. It's been optimized specifically for LOINC. And OCL Mapper is a general purpose tool that we have not yet supported things like unit translation, LOINC optimized search, so like all of the presets for checkboxes that make it really quick to narrow in on certain searches. Some of those still need to be adapted and implemented, and we look forward to collaborating with you to get a lot of those over there. So this is an AI-capable matching tool. So what does that AI-enabled workflow look like for terminology mapping? So once a user submits the auto match in the back end, we implement a well-adopted AI paradigm of pre-process, retrieve, recommend. And so pre-process in the terminology world means we're doing context setting, cleaning, keyword expansion, entity extraction. On the retrieval side, we're using a number of different methods that we already showed, like lexical and semantic searching, the bridge terminology searching, and others. And it's a multi-retrieval method, so multiple algorithms can all contribute to a common candidate pool. Then the recommend stage. Well, there's traditional approaches around compound scoring and re-ranking, but now we have new methods as well, LLM as judge, where it's not supposed to generate new content, although that's not easy to control all the time. It's just supposed to evaluate your candidate pool and evaluate it and give you recommendations. And then that candidate pool is then returned to the user in their user interface, and they can actually start the collaborative review process. And that's where we get to some new exciting capabilities. And again, a lot of the work that we're doing, some of it's already in the OCL Mapper, some we're doing in what we call the sandbox, which is where we're collaborating and experimenting with these methods. So the agentic copilot would be one of those, where as you're working through your project, it's learning what you're doing, learning about your context, and able to improve its recommendations throughout the project. And finally, once your decisions have been made, those mappings contribute back to the pool and make the whole process a learning system that gets smarter. So we did an evaluation, and thank you to Pam Banning for preparing a validation data set for us from the top 200 LOINC codes and formatted those into an unmapped lab catalog. And we put that through our process then. So we used 3 algorithms for retrieval, a semantic search one from that OCL supports, the CIEL bridge terminology, which would add that lexical variance that we talked about. CIEL has about 1,000 maps to LOINC, so it can expand the synonyms that are used, and it also is doing semantic search on those. And the third is SciSpaCy. So SciSpaCy is an existing language model that Dr. Venkat Sengam and Parvati Menon from IU, Indiana University School of Informatics, adapted specifically for LOINC, that it does UMLS entity matching to LOINC parts, and it uses a novel reassembly method to define LOINC candidates by reassembling those LOINC parts. Those all contribute to our pool, and those are passed on then to an AI assistant that evaluates them and comes up with its assessment of recommend, conditional, or reject, plus additional rationale. So over the results. So each algorithm contributed 10 results. And you can see the bottom 3 here are the individual matching algorithms. That each one, the top N metric is a standard that says, was the correct match in the top 5 or top 10 candidates returned by that algorithm. So the individual algorithms, as we expected, each one contributed about 35 to 50% of the correct matches to the candidate pool. If those were all finding the same candidates, we wouldn't be doing very well. But fortunately, because of each one has a different methodology, they find different candidates, which means when you put them into a common pool and aggregate the analysis, it pushes it up to that green line. So we get up to 86% of the correct matches were in the candidate pool by combining the 3 algorithms. Let's look at a couple specific examples then from this data set. This is the BNP test. So already retrieved the candidates, we handed those over to the AI assistant, and it made its conclusion. It said, we have a strong recommendation. And so what is that? It's that it identified the exact component, system compatibility, matching units, and strong algorithm consensus. So this is one where all 3 of our matching algorithms were able to identify this one. It also said, hey, this has got a high common test rank, and here's a verification step. Let's make sure that you, as the user, as the mapper that's using this tool, verify the units. And so if we were to grade the AI assistant on this, I think we'd give it an A. We'd say, the right content was in the candidate pool, the AI assistant judged it correctly, and it also explained the matching access and gave verification steps, and those were kind of the key points that we wanted. So let's look at another one, globulin. And I am not a lab expert, so you'll notice that as I'm reading through these rationale. But so the input term globulin here with system serum creates ambiguity between gamma globulin and total globulin. But it does have 3 candidates available now. And so you can see on the left, the AI assistant said, well, this is conditional. We don't have enough metadata or knowledge, it could be one or the other, to make a strong recommendation of a single candidate. But it did come up with a primary and alternates, and it gave you guidance as a user on what's the decision point, what verification process do you need to follow in order to identify the right one, which is exactly what we would want it to do. And so does your local globulin term specifically mean gamma globulin from SPEP, or does it represent total globulin? And with additional verification steps. So again, I think we would say candidate pool, A, the match was there. The AI assistant, A, it correctly said this is conditional, and identify the right alternates, and gave you verification steps, which again is what we wanted to do. So a third example though of urinalysis, white blood cell, test description, that all current candidates have system, white blood cell, but the input term clearly is specifying that this would be in urine. And that was not available in the candidate pool, so it rejected all of the candidates and gave you direction then, what should you be looking for? Search for LOINC codes where system equals urine, component equals leukocytes with the specified counting properties. So I think in this case, we'd say the matching algorithms did not do their job, so we'll give them an F, but the AI assistant did what we would hope it would do, which is it rejected them and gave you direction. One final one where the AI assistant did not do quite what we expected is with 25-hydroxyvitamin D. It strongly recommended a LOINC code, 622928. That ultimately was not the correct one. And it did provide key verification steps, and I think these were spot on, that identified the alternate and said why you would want to choose it. So if you followed the rationale, you would land in the right place. But we wouldn't want to do a strong recommendation if it's not able to, if it's actually ambiguous. So here we'll say the candidate pool again, we get an A, but the AI assistant gets a B because it did not do the correct match, and it made a strong recommendation, but it did provide guidance. So I would have given a lower if it didn't provide good guidance. So if we put all these together across the 200 rows, what were the results? And I wish we could go through more because I think the rationale is a lot of fun to review. But what we found here is that the correct match was identified, assuming it's in the candidate pool. So out of the 200, there were 172 times that the correct match was in the candidate pool. And it got 151 of those right. So that's 88% of the time it identified the correct match in either the top spot or the alternate spot. And when it wasn't in the pool, it rejected it only 11% of the time. So that's not great. We would like to do better on the rejection side. AI, as you probably all know, does tend to be overeager. It's sometimes hard to rein it in. It really wants to give you what you ask for. So the incorrect AI recommendation, so this is just the inverse of that top row. I highlighted this because this is what's actionable. So if we can track the number of times that the incorrect AI recommendation came out when it was available, that's the number we want to focus on for performance improvement in the future. But the AI assistant can do a good job if the match isn't there, right? If the candidate's not available in the pool. So that's focused on the match algorithm, right? So the correct match was in the candidate pool 86% of the time, and then 14% of the time it wasn't. What's interesting is for this latter one on the candidate pool, this is already a well-defined space. Deterministic methods and AI methods for generating a candidate pool that does a good job. Like we included only top 10, you could expand to top 20. You could evaluate that. You could add a fourth algorithm on it. You could do a better job with some of the other steps that were in that process, like pre-processing, to really get that number in a place that we'd like to see it at. So the discussion here is like, what worked well? Multi-algorithm retrieval demonstrated a ton of value, that each one was contributing different pieces, different candidates to the pool. We look on the right there in the table. I know it's small, but this is the number of candidates that were only provided correct candidates that were only provided by one algorithm, which shows the value of combining multiple approaches. So that was nearly 45% of the candidates only came from one of those algorithms. So that approach is great. The second one, I've talked a little bit about the overeager AI behavior. And with LLM as judge, you really want to restrict the behavior to focusing just on reviewing your content that you gave it. And so an interesting way that we can do that is by saying, well, if you're going to be creative, let's create a box for it that's outside of the structured ones that I really need you to be accurate and precise on. So it's providing a top candidate, alternate candidate, and then it has a little space that if it wants to be generative, it's called out of scope. And we didn't talk about that today. In about 10% of results, there was an out of scope narrative that was provided that in some cases was actually interesting. This is called generative judgment, and it's a known behavior. And it's not necessarily a bad behavior, but it is something you want to control, especially if you're trying to automate workflows in your architecture. So the next thing is that the results that we showed are very dependent on the input data set that we showed and the target repository. So, in this case, the LOINC. And that a lot more work and evaluation needs to be done to see, how well do these algorithms behave with different data sets and repositories. In our practice to date, sometimes it does really well, sometimes even better than this, and sometimes not as well. There's some universal improvements that we can make that, if we make it, it'll work for all data sets and all terminologies. And the most exciting one here is because I talked about the MCP. I did that because it's clearly the next step for this. The AI is often going to know when it's doesn't have a strong recommendation. It already has that score. And it's either rejected it or it said, we're not very confident about the recommendation we're making. What if it also had access to tools where it could do its own follow-up searching directly using these algorithms and using direct searching of the target repositories? So with an MCP, this is very possible, but you need an agentic orchestration layer that's connected to the search to make that possible. So that's where this would go next. And there's also plenty of room for LOINC-specific improvements. And I think this is exciting because these results aren't bad to date, but it's also the worst that they will ever be for LOINC matching because all of these are improving rapidly these days. And so for ones when we didn't get the right match in the pool, the lowest hanging fruit is pre-processing. So what about unit translation, or when there are symbols in the names and descriptions that could easily be translated to improve semantic search performance? So that's a low hanging fruit that would result in improvement. Another one is that having more context for the AI so that it knows more about specific LOINC modeling and specific LOINC mapping recommendations and rules. So that's kind of one of my conclusions of this is that a recommendation for the LOINC community is that develop LOINC-specific context and rules that is a public community artifact that's maintained and evolves along with LOINC releases. And that would be declarative as necessary and AI supportive, provided some the obvious simple examples at the bottom of what it would mean to have a declarative rule that an AI agent would be able to follow. And this wouldn't be just used by the OCL Mapper. Anyone that's using AI with LOINC could benefit from having those types of rules that they could load, with just by pointing to a URL, load into your AI context, and suddenly you have an AI agent that is much more capable with LOINC. So I want to switch now to my colleagues Joe and Michael. I think maybe you can both come up now. And so Joe is going to provide a demo of the actual OCL Mapper, and Michael is going to talk about some stories from the field of where the OCL Mapper is already being used in some global health contexts and some value that they're getting out of it.
Hi, glad to be here. I got the fun job for today. I get to come up here and show you this cool interface and then peace out before you start asking hard questions. So John has already talked us through a decent amount of what this workflow is going to look like. I generally just went ahead and loaded this up for the sake of speediness. So I'm going to show you how I configured this, but I want to go ahead and hit the go button before we're doing anything else. We're essentially already going to tell it we are trying to match to the latest LOINC version here using this search algorithm, and that we're going to want candidates, and we're going to do all of our pieces here. So we're hitting go button, and now I can talk through a little bit of what's here. I have pre-configured this mapping spreadsheet, and this is exactly what John was showing before with the same rows. It's orders, it's got tests, it's got some context, but certainly not as descriptive as a LOINC concept would be. I have brought this in under my own ownership, meaning this is under my user profile. But if I so chose, I am on multiple teams that I could be sharing this with and doing a collaborative work with. This does not just have to be me. This could have multiple people on it. Again, I brought this in just as an Excel spreadsheet. You can do CSVs and whatever you want. We are matching specifically to LOINC, and I particularly will be focusing on English names, although some might be looking for different translations. And I've applied a filter just that we're only going to be getting LOINCs. I'm not looking for parts, I'm not looking for lists, I'm just looking for LOINCs. And then I have also configured the score algorithm to give me 70% or higher. This is kind of the default. I just want good matches in general. As far as these inputs, I'm only really setting up 4 of them as good matching pieces here. And so I'll actually close this out so you can see them a little bit better on through this table. Essentially, this is here as context, our order description and our order mnemonic, but we have set it up so our specimen field is mapping to LOINC's property specimen. We are using the mnemonic as just as a shorthand, kind of a synonym, and really the LOINC name is matching up with our test description. I also gave it a method over here, although there are certainly fewer methods. So while this has been going, and again, this is thinking as we're going through this because it is evaluating each of these and giving it some real thought. This is not quick keyword matching. This is actual good thought that's going into it. And we've already got a few ideas, few proposed codes here. One of them is this example that John showed a little bit earlier. And I want to show the kind of thinking process that we're going through as we start evaluating this and how we get some help from AI. So here's our source code. We are 25-hydroxy vitamin D here, and we've been given this first proposed mapping to 109073-7. If we want, we can take a few looks into this to try to see, is this hitting what we're trying to hit? We see some attributes down here, and we can see some of the score and matching results here. If it's something that we're feeling confident with, we can make the decision. We can decide, is this something that is decided? Right now, we have it as proposed, but if it's something that we're feeling more confident, then we can start mapping. In some cases, you might want to exclude a row from mapping because it's clear that it is not something that is meant for this. It's not something we need to map right now. Before I do any kind of approval or rejections about this, I actually do think it's going to be good to start looking into the candidates. And as we can see here, we're getting a little preview of this particular LOINC that it was provided right off the bat. And I can go ahead and click on it to just start getting some more details about it. And we have a good amount of properties in here. We've got its long common names, all of its 6 axes. We've got definitions, especially we've got some names and synonyms in here. For the concepts that do have translations, you would actually be seeing a long, long list of the different translations that pop up here. And if there are associations, then you might be seeing those too. So in this particular case, we've only got a parent part, but in many cases you might see previous concepts that were mapped to it. If there's elements, if there's associated observations, these are all things that you can see in the details of the concept and start getting an idea of if this is the right match for you. Now, to be clear, I'm not clinical, I'm not lab, I don't know enough to make any kind of decision here. I've got this little guy here who's going to come in and help me out, and he's going to do some thinking while we just look a little bit more of what we have here. You can filter down candidates if there's specific pieces you're looking for. Maybe you want to filter out anything that's deprecated, discouraged. You want to filter out anything that is, for example, maybe you need either both or you need observations. Maybe these subsets are totally out of scope. One cool filter I particularly like, and this is when the metadata is more enriched, there is a mapping target repo down here just to say we're looking for concepts that are already mapped to another source. In this case, we don't have a longer list. We only have the internal mappings. But if you're looking for more commonly mapped concepts, then you might be able to do the filtering down here. So just to say that we can see exactly which candidates we want. In this case, we are getting a recommendation in here, and it is actually not the top proposed candidate here. And as I'm kind of reading through, like, all right, AI, what is your recommendation here? I see some things that I'm also liking. It has a high clinical usage rank. It's 194, it's an active status, and a few other things, which not only is helpful for building confidence in this one particular mapping, it's also teaching me as a non-clinical, non-lab person what kind of things are helpful in doing mapping in this. So in this case, it has given the recommendation. We do 62292-8. I'm going to go in here and just look a little bit, and you know what? It feels right. I'm going to verify. I'm going to use that as our mapping now, and that is something that I could go ahead and approve. Now, one thing that I also want to note about this whole thing is that this is a collaborative activity in many cases. It's something where you might want to keep your history. You might want to share with someone what decisions have been made already. And you can see this history in the Discuss tab over here, where we were given an auto match. We asked for an AI recommendation, and we got it. And so, all right, I have decided that we are going to go with that, and we are going to hit the approve button. And this is kind of the history, the journey that this has gone through. If you have a team of people working on this, multiple people will come in and say, all right, I think it's this, or I think it's this. And so you're given that space to do so. If you didn't like the candidates, you also are able to just do some global searching yourself. If you need to do a little bit more specified queries in here, something with specifically blood or whatever it might be, you can get the results that you think are going to be more correct. One other thing that I particularly like is this propose part here. Propose is for when essentially you didn't find what you were looking for in the terminology and you think it should be in there. This is where you start to basically say, all right, here is what I think should be part of the LOINC terminology, and I could fill this out, add some notes, and get it ready for submission to LOINC itself or whatever source terminology you were using here. So you would be going through this workflow for, right now we've just approved the one, but ideally you are going through this quickly, one after another. You're able to see these and kind of verify somewhat quickly. If it looks exactly right off the bat, great. We approve it, we go on to the next. Now we're looking at the next concept here and begin doing our mapping one at a time. If it doesn't feel right, I didn't like maybe the recommendation made, then I'm just going to say reject, and we're going to move on. And as we work through this with our team, we can start to see which things have been approved, which things are proposed, which things got rejected, and pieces like that. Once you are done with your project, of course, this is in our browser. It's something that we are saving as we are going. You also are able to download this entire project as a CSV file, start sharing it around with the people who need to see it, but maybe don't have an OCL account or whatever it might be. So there's quite a few things you can do in here, and there's much more we would like to talk about later. Just most importantly, we're getting the help that we need both in the workflow and from someone who's a little bit more familiar with labs than I am. Okay, Michael, are you ready to come on up and talk through some real-world use case? Mm-hmm.
Sure.
Okay.
Thank you, Joe. How much time do we have? 5 or 10?
We've got a couple minutes, yeah.
All right. So I'll share with you some stories, 2 stories actually from the global health use cases. One with MSF and one with a small NGOs that we have in Burundi without any terminologists, without any knowledge in concepts. So the first story that I have is about a project with MSF in general. And the context was about, okay, we need to build 50 new clinical forms for 50 new programs in English and Arabic in less than 1 year, which sounds like a lot of time, but actually the usual average to build a new program is about like 2-3 months. So there was quite a challenge. So what we decided to do actually about one year ago is to get together with Andy Cantor from CIEL, with Joe and John's team from OCL, the OpenMRS team as well, Madiro and MSF, and Regenstrief, and start looking into this idea of a mapper. So the first solution that we decided to go with is, of course, the existing OCL platform. It's something that we've been using, I think, for like 6 years now in production, deployed in Bangladesh, Afghanistan projects, all kinds of projects and programs. So that was in place. The second thing is the OCL Mapper, so that we actually started looking into more than a year ago, and we developed and started using it along the way iteratively. The third solution that we also started using is the OCL MCP that John mentioned earlier, which is this tool that allows you to discover your content and also potentially take actions on it, like the translations example. So I won't go into those videos. We have a roundtable later on, so if you have any questions, join us, and happy to dive into hands-on examples, but they will be in the presentation. So before we started, like I said, the average time to build forms, and only one form, if you take like, I don't know, MHPSS baseline assessment, for example, in mental health, or maternity form, anything, it was about like 23 days to build one form, because you have like hundreds of terms to map. That was 1 year ago. And then we started exploring this mapping tooling and a first prototype of the OCL Mapper. So we were able to do semantic search. When you think about the comparison and the features that we have in the OCL Mapper and OCL Toolkit today, that first one of the semantic matching helped us to reduce that time to like 15 days per form, which was already not a big save, but already really significant. And then we had like the next version of the OCL Mapper that changed a lot of things. Like this UI that Joe was just demonstrating really changed everything, because the content manager and the clinical team were able to see their percentage and make choices and decisions with more confidence. And the UI is made in a way that it can go really quick through the results. Like you can use the arrow of your keyboard and then go through really quick and make better decisions on the mappings. So it dropped the number of days to like 2 to 3 days per form. That's the time that we take these days to actually create the clinical forms at MSF, and also with the help of the OCL MCP. So for example, I can take one schema of a form, like a draft, drop it in the MCP tool, and then it will tell me which concepts are missing really quick. So I don't need to go in the platform and then search for the terms. No, the MCP will do that job for me, and also for the content managers. So that's the first example I wanted to share. So significant reduce in time to develop the clinical forms, about like 80% time saved. Also a reduced risk of errors in the terminology usage itself, reduced by about 30%. So we measured that using the feedback that we got on the forms themselves, or when we were reusing the concepts and the terminology. Increased reusability, which was also the initial reason why we started working with OCL, is to allow us to reuse terms and forms across project at MSF and not have siloed implementation of clinical forms. So now there is an MSF-wide source and collections, NCD, antenatal, anything like that. Of course, increased possibilities of interoperability. So we have direct individual data exchange with the HIS2 automated, and also lab. And better scalability across project, like all the collections that we built using OCL tooling, so the Mapper, the MCP, and the platform, is a pathway to scale to 60 projects that we have in the scope. And the first one I didn't mention, but the first one where we started is a project in Mosul, Iraq, for this one. The second story that I want to share really quick, it's a really small NGO, local NGO, but it's a really interesting use case, because I think it was Stan earlier who mentioned, like, what if you don't have terminologists? What if you don't, like, and John, you mentioned that as well, like, we have unicorns in the room, but what if your local team doesn't have that knowledge? So that was a really good use case for us to show how OCL can actually support that and bring this confidence and knowledge to teams who don't have that. So the context is no terminologist, no content manager, only one data manager, and doctors and clinical team. So that's the first piece of context. The second is the team had less than 2 months to simply go digital. They were like paper-based, and the Ministry of Health came to them and say, okay, if you don't go digital, we cannot fund your under 5 and maternal care. So the clinic was simply at risk. So in this hospital in Burundi, rural hospital in Burundi. The third piece of context is French and English were required. So again, the content to map, pretty usual use case. So about 300 drugs, 100 lab tests, 150 procedures, and about 1,000 diagnoses, because they are mapped with the Ministry of Health at a national level. And also the idea to allow for data exchange with DHIS2 again, and the community health workers. The results, and just before I jump into this, this digitization, before we started using this tool, the director of the clinic was like, oh my God, how will I do this? This is impossible. Then we introduced him to the OCL Mapper, actually the previous version. And he did this job in just like 2-3 days going through. I was like, you did it? He's like, yeah, it's good UI. And he just did the mapping by himself. I was like, okay, good. And it was actually the ultimate goal for us. This was for this team to gain ownership on their content, but understand the structure of their concepts, and yeah, give them a tool. So the good news is that we got a successful validation from the Ministry of Health in June, back in June. And the the maternal care and under 5 care are now funded by the Ministry of Health. So the clinic is now more sustainable and don't rely on external grants for that. And also a big one is unlocking the next step for interoperability, because we got, of course, like collaboration opportunities with people saying, oh, we will connect with the community health workers and DHIS too and everything, but we all know, like, if you don't have the right mapping, how do you do that? And so this concrete step of mapping really unlocked this step of exchanging data for them and for the community health workers. So better continuum of care, basically. That's it. Over back.
And so just to close out briefly, because I know we're at time, the tools that we've just introduced, I hope you can see that we're kind of marrying a lot of technical expertise with impact orientation, and this was a wonderful example of that. The tool, the hosted version of this tool is going to be available soon. We encourage you to sign up if you'd like to be on an early access wait list, because well, basically the infrastructure costs are high and the compute expense, is high. We want to roll this out and make sure that the platform stays stable. And there is a roundtable discussion this afternoon at 3:30. So if you'd like to continue the discussion, please join. We would love to do that. So, all right, thank you so much for your time, and it was great to be here.